Okay, so if anybody comes in late, I want you to tell them that this was like the best talk you've ever seen, and they'll really regret not coming in to see my talk. Anyway, so what we're going to talk about today is order revealing encryption. The basic client-server architecture is used pretty much everywhere. There's a client that generates data and interacts with the server, and the server stores this data that's generated on some database. This model is ubiquitous throughout computing and works pretty well generally until there's a breach and the confidentiality of all this data that the client put in the server is compromised. Despite advances in our understanding of how to prevent these breaches, they still happen with alarming frequency. So having a way to protect the data, even in the event of a breach, is desirable. One seemingly obvious solution is to encrypt the data on the server with a key that's only known to the client, using some kind of standard AES, ASGCM, IND, CPA, standard encryption. This method preserves the confidentiality of the data, but unfortunately it doesn't enable any kind of application functionality. The data basically just sits there and you can't do anything with it. In the last 15 years or so, the cryptography and the systems communities have been working on encryption schemes that kind of strike a middle ground between full security and full functionality. In this talk, we'll call them property-revealing encryption schemes. These allow certain properties of the data to be leaked to the server in a way that enables certain application functionality. One of the most exciting and most widely studied such primitives is order-revealing encryption. There's been a lot of interest from academics in the last few years, and there has even been interest from industry and from government. So it's important to understand the security of this primitive. So the functionality of order revealing encryption is pretty simple. The client inserts some encrypted value, and the server can non-interactively reveal the order of that value relative to the other ciphertext in the system. This allows it to basically maintain a sorted data structure of ciphertext, which it can use to efficiently answer things like range queries and group by limit queries in SQL and stuff like that. These order-revealing encryption schemes are proven secure, but they don't satisfy standard cryptographic notions of security like semantic security. Instead, they're proven secure relative to some amount of leakage about the underlying plain texts. So the question we really want to answer in this work is, what is the impact of this leakage on the security of ORE when it's used to encrypt real data? In this paper, we work toward answering this question by developing new leakage abuse attacks, which basically, in aggregate, attack all existing ORE schemes. We empirically tested these attacks by doing experiments on real data. And for first names, we were able to recover up to 99% of the encrypted values in a simulated encrypted database. For last names, we were able to recover up to 97% of encrypted values. And for birth dates, we were able to recover up to 90% of encrypted values when they are encrypted with the ORE scheme most widely used in practice. We also explore known and chosen plaintext attacks against ORE. We're the first work to do this, and we show in the paper that basically a small increase in the amount of knowledge that the adversary has can be catastrophic for security. Unfortunately, I'm not going to have time to talk about this, so you can see the paper for more details. So before we describe our attacks, we have to kind of define what a leakage abuse attack is. A leakage abuse attack is a cryptanalytic attack against a PRE scheme. And contrary to other kinds of cryptanalytic attacks that attack the assumptions of the cryptography, we don't attack the assumptions. Rather, we just attack the inherent leakage of the PRE scheme. The various different kinds of ORE schemes that have been proposed all have different kinds of leakage. They all, for correctness, have to leak the order of the underlying plain text. Some of them leak the order and the frequency of the underlying plain text. And some efficient schemes that have actually seen deployment in practice leak the order, the frequency, and some of the bits of the plain text. Our leakage abuse attack is going to combine this leakage with some auxiliary data, which is basically just a model of the distribution from which the plain texts were drawn. And in this work, we're going to use public data as a stand-in as the auxiliary data. The goal of a leakage abuse attack is basically to recover some plain text. And we're going to call the recovery rate the fraction of plain text that we guessed correctly. The first attack we're going to discuss is against the schemes that leak both order and frequency of the underlying plain text. The leakage here, again, is basically in this simulated database, the leakage is the order of all the values as well as the number of occurrences of each particular ciphertext. So for example, the ciphertext corresponding to the encryption of 4 appears 5 times, and the encryption of 3 appears twice, and this kind of forms a histogram that's revealed to the attacker. In our attack, we're also going to take our auxiliary data, which is kind of a model of the plaintext distribution. Note that in these attacks, it's not all plaintexts are encrypted in the database. If this were true, it would be trivial to recover all the plaintexts all the plaintexts in the database by just sorting the ciphertext and the plaintext, or not the plaintext, the auxiliary data, and just matching equal rank elements in this list. And this is basically pointed out by prior work. So there are going to be some elements in the auxiliary data that do not occur. That is to say, their ciphertext there are no encryptions of these elements in the database. But crucially, we don't know which elements these are. So prior work at CCS 2015, Naveed, Kamara, and Wright presented an attack against this leakage, which they call the cumulative attack. It uses what's called a linear sum assignment problem, which is a kind of standard problem in optimization to kind of model the plaintext recovery operation. I'm not going to describe in too much detail what they actually do. It's a little technical, but basically what they do is create a matrix of costs which represent the cost of mapping ciphertext to plaintext. And the elements in this matrix are basically generated using the relative frequency of the elements of the ciphertext in the auxiliary data. Once they create this cost matrix, they solve it using a known algorithm from the optimization literature called the Hungarian algorithm, which requires qubit time asymptotically, which can be a little prohibitive for large data sets. In the course of doing this work, we noticed something about the cumulative attack, which was a little odd. Basically, the cumulative attack, while it does incorporate the order of the elements in a way that I won't go into, you'll just have to take my word for it, but while it incorporates this in the cost function, there actually aren't any hard constraints on the solution that's returned from the algorithm, which means that the solution that's returned, the mapping that they get from the Hungarian algorithm can actually have crossings. And what this means is basically, if you think of the solution that's returned as basically the lines going from the auxiliary data to the ciphertexts, the plaintext of 1 could be mapped to the ciphertext of 3, even though the plaintext 2 is mapped to the ciphertext of 1. Now, this obviously violates the known ordering constraints on the problem, the known ordering of the auxiliary data and the ciphertext. So this suggests to us that we aren't really, the cumulative attack isn't really using the order leakage to its fullest extent. So in our non-crossing attack, we view the problem slightly differently. Rather than treating it as an optimization problem, we view it as basically a weighted bipartite matching problem. So what we're going to do here is create a bipartite graph a complete bipartite graph where each auxiliary data corresponds to a vertex on the left-hand side, and each target data corresponds to a vertex on the right-hand side. And we're going to weight the edges using, again, some frequency information, which I won't really go into. Now, this view of the problem isn't really that exciting or new. In fact, it's pretty much a trivial consequence of the old optimization view. But what it allows us to do is basically express the order constraints on the problem as a graph constraint on the matching that's returned by our algorithm. So what we want to do is, rather than search through all the matchings to find the best solution, we're going to search through just the matchings that have no crossing edges. So what this enables us to do is use a known algorithm from the graph algorithms literature and find the guaranteed best matching in actually asymptotically faster than the cumulative attack, using a kind of very basic dynamic programming approach. To test the empirical performance of this attack, we used public data as stand-ins for the kinds of sensitive data people want to encrypt. For first names, we used about a dozen data sets of public employees drawn from, I think, a few different states and maybe one federal database, as well as a database of police officers that was leaked last year. And we also did attacks on zip codes and birth dates, and for this we only had one data set, which was the police database leak. And for these attacks, because our auxiliary data wasn't very well correlated with the target data, they didn't perform particularly well. If you want to see more information, you can see our paper. And for the auxiliary data in these attacks, we used public US Census data. So the NKW cumulative attack recovers about 44% of first names on average. Our non-crossing attack recovers almost twice as much, 83% on average. For last names, we actually couldn't get the cumulative attack to run in any reasonable amount of time for any of our last name data sets. Our largest problem instance, I think, had around 17 billion edges in its graph, and the order n cubed runtime just basically makes the Hungarian algorithm choke. So what we did was instead used a known heuristic from the graph algorithms literature that allows us to get a approximately optimal mapping in order n squared time. And using this and the same weighting function as the cumulative attack, we were able to get about a 5% recovery rate on average for last names. This suggests, or this data shows basically that the non-crossing attack is about twice as good as the cumulative attack for first names and about 7 times as good for last names. Another advantage of this attack is that it basically makes it very easy to incorporate the additional leakage of some of the more efficient schemes that are used in practice. So what you just need to do is take your bipartite graph that you start out with and remove the edges that contradict the additional leaked bits of the plain text. So for example, if you learn that the top bit of this particular ciphertext is 0, what you can do is just remove the edges that would map it to any auxiliary data whose top bit is 1. It's pretty simple. So this adaptation of the non-crossing attack with the additional leakage of the ORE scheme most widely used in practice lets us recover about 99% of first names on average and about 97% of last names. And with the leakage of the recent ORE of Chinet et al. From last year, this allows us to recover 98% of first names and 75% of last names. So now we've kind of seen the attacks that take advantage of order and frequency. But now we'll look at an attack that just takes advantage of the order, which again, all ORE schemes leak just by correctness. The schemes that actually achieve this low level of leakage are pretty inefficient. They require either strong cryptographic assumptions based on multilinear maps or stateful interactive encryption protocols with client-side state. Nonetheless, it's important to study this setting because all ORE schemes leak the order of the plaintext, so attacks in this setting give kind of a generic lower bound on the security of any ORE scheme. So in this attack, again, we're not going to have the frequency histogram of the ciphertext. Instead, what we're going to have is basically just a sorted list of ciphertexts where encryptions of the same plaintext are going to be in a contiguous sub-interval in this list. So it's useful to think of this as just kind of a number line where the least ciphertext is on the left here and the greatest ciphertext is on the right. The basic idea behind our attack is that the position in the list leaks information about the underlying plaintext of a ciphertext. So to illustrate this, let's just think about the ciphertext of the name Aaron. If we want to look for the ciphertext of Aaron, we're probably not going to look at the end of the list because most names lexicographically are greater than Aaron. Instead, we're going to want to look at the beginning of the list because it's likely that in any sample, most of the names sampled are going to be greater than Aaron. So we're going to use this intuition to build our attack. At a high level, our attack basically just tries to locate the range of ciphertext that all correspond to some given plaintext value. For example, if we want to recover Michael, we just need to find the range, we just need to find the first ciphertext of Michael and the number of Michaels in the database. And we can find the range just by taking the first value and adding the number of things, and this gives us a lower and upper bound. Finding the number of Michaels is really simple. Basically, if you have your auxiliary model, what you need to do is just multiply the frequency of Michael by the number of ciphertext in your database, and this gives us basically the expected value of the number of Michaels in your sample. Finding the first Michael is a little bit more complicated, and what we have to do here is basically consider all of the plaintext that are encrypted in your sample as being split into one of two groups. Each plaintext is either strictly less than the name Michael, or it's greater than or equal to Michael. This allows us to basically treat the problem as a kind of binomial distribution, where we have a coin where heads indicates that the plaintext is less than Michael, and tails indicates that it's greater than or equal to Michael. And we can estimate the position of the first Michael just by flipping this coin for each plaintext in the database. The attack finishes by basically, the attack that I presented is just for one name, but to attack the whole database, what we're going to do is choose a certain number of high-frequency elements according to the auxiliary data. Intuitively, we want to do this because the ranges of these elements are likely going to be the biggest ranges, and even if we miss some names, we're going to recover most of the names corresponding to that element. So when we do the top 40 names, as I just described, for first names, we recover fully 30% of the values in the database on average. For last names, we recover about 7%. This seems a little meager, especially compared to the very exciting 99% from before, but it's interesting to think that this is kind of like the absolute minimal leakage, and yet the recovery rate basically is about 7 times higher than the baseline accuracy. And here, when I say baseline accuracy, I basically mean just guessing the most frequent element of the distribution. So just leaking the order makes this basic attack about 7 times more effective, which is kind of a lot. So in conclusion, the security of ORE for real data that people actually want to protect in practice is substantially worse than I think anybody feared. Now, there are some limitations to these attacks. The attacker especially needs good auxiliary data. Our zip code and birth date attacks didn't have very good auxiliary data, and they didn't perform very well. Just for other researchers, I think more work is needed to understand the power of leakage abuse attacks against both ORE and against more general PRE schemes. And just as a final takeaway, if you're considering using ORE in a project or in a commercial product or anything like that, the only place that it's appropriate to use ORE is if the only other choice is to use plain text because of legacy constraints or application constraints or something like this. Basically, if there's any other choice, ORE should probably not be used. So thanks for listening. Any questions?
Hi, thanks for the talk. I have one question regarding the top 40 names. Mm-hmm. How many names were there all together, and do you have any idea if you used all of the names, how much it would drop?
I'll repeat your question?
You only used the top 40 names to guess. And do you have any idea if you would use all of the names, how much it would drop, and how much the overall probability for all of the names would be?
No, that's a good question. So his question is basically like, so if we use all the names, we're not going to estimate all the ranges correctly, and we expect the recovery rate to go down. The answer is I don't know. I haven't tested it. I'm not sure how much it would go down. We can talk offline. I haven't thought about it, but.
Okay, let's thank the speaker.